So I'm going to turn on my lovely video analysis tool. There we go. We're going to look at a basketball shot. We're going to take the example video as a basketball shot, and you're going to see why it's important to have an object that's in there. But my basketball shot has motion in both the Y direction, up and down, and has motion in the X direction. And we're actually going to look at that. So I got my lovely basketball shot here. Now, to make this realistic, I've got to have a known point of reference in my picture. And I'm going to have to give my video some information in order so that it can actually make this data more realistic. So in this picture, I really don't have anything other than my door. And I can use this, and I can put in a ruler here. And I can actually use that straight line as a known distance. Because basically all I've got up at the top, it says my unit are in pixels, which are the little dots that make up the image that I have. Turns out doors are roughly about 7.5 to 8 feet. So I'm going to use 2.2 meters just so that things are a little bit more realistic in here. And so I'm going to type in my 2.2 meters, and I've got my door frame that's there. Now we can set up our coordinate system. So I'm going to give myself an origin. I'm also going to move my video such that the basketball has left this person's hand. And once the basketball has left that person's hand, I'm not imparting anything to make that basketball go. Once it leaves my hand, it's going to be traveling at the same velocity that it gets once it leaves my hand. Now, there is an acceleration that's acting on the basketball, and that's the acceleration due to gravity, which is acting downward. But that's only in the Y direction. And we're about to see that the motion in the X direction and the motion in the Y direction, up and down motion versus left-right motion, are independent of each other. The basketball is going to behave in the Y direction differently than the basketball is going to behave in the X direction. And that's why we get projectile motion. I'm going to have that difference in behavior. So in order to do this, we're going to start getting data points. And we can actually click on our image to get data points. And there's going to be some experimental error in here because we're having to guesstimate the approximate center of mass of our basketball. And our basketball gets a little blurry. So as you start thinking about what you want to video in terms of the video, the bigger the object, the little easier it is to kind of get data. The red line, the red dots are motion in the X direction. The blue dots are motion in the Y direction. It's clear that there is something different between the X direction and the Y direction. And that difference is there's no acceleration in the X direction. So my x is gonna equal my velocity times time at any point in that video. Wherever it is on x, once it leaves my hand, whatever component of velocity that's in the x direction is gonna stay constant throughout the whole thing. And I get a nice straight line. And the slope of that line is that's a position versus time graph. And we've already talked about it once or twice, or maybe 3 times at this point, that straight line tells me I'm at a constant velocity. Well, I don't have the same thing happening in the y direction. Don't have the same thing happening in the y direction. I've got an acceleration. So as I am moving up and down, that acceleration is what's going to cause and give me that parabolic movement that I get. And projectile motion is going to look like a parabola, just like what we see with that basketball. So we're going to see that particular basketball. I'm going to do something else for grins and giggles, just because it just occurred to me. We're in an experimental class, so we're going to try it. This is the better one. I'm going to download this. Makes sense. So I'm going to import a video. That's what we're going to do. So I got a video here. Happens to be my grandson from 2 years ago. We are on a train. We happen to be somewhere in New Mexico. So you can kind of see the background. You have to be somewhere in New Mexico. So we're going to do an experiment. He's going to toss that lovely stuffed animal, which happens to be an okapi. You know, if you're not familiar with okapis, okapis are cute little critters. The Oklahoma City Zoo has them. They're very soft. They have unusual features, like they can retract their eyes completely in. They can retract their eyes. They can actually clean their eyes with their tongue. They are, the closest relative is a giraffe, and they are actually sometimes called the jungle giraffe. So if you want to know more about okapis, I can give you all kinds of interesting okapi facts. So that's an okapi. We go in here and we're going to get this up. We're going to toss our okapi up. He's also going to jump. So we've got the start of the video there, where the okapi is going to leave his hands and is going to go up, and we're going to actually do the video analysis. So I'm going to give myself a system. That's probably about 0.75 meters. Just remembering what my dimensions are in my, because we're just going to look at the behavior. We're going to start with our origin there, and we're going to follow our lovely little okapi. And we're going to try to go from the center of mass of our okapi. So that's probably good enough. So given our situation, looks like we stayed in place. But did I stay in place? Did my grandson stay in place? We're on a train. We're moving down the railroad tracks at about 65 miles per hour. But the way our image here is, it didn't matter. Everything was moving down the railroad tracks at about 65 miles an hour, and we only went straight up and straight back down. Now, we still had acceleration due to gravity, which is why we get my little arc. Because I'm looking at my position in y versus time. But if we look at it, we just moved up and down. So my position in the y direction is very different than my position in the x direction, and they're independent of each other. But this one clearly shows that we, relative to the train car, we didn't move. But the whole train car is moving, and we are in that independent motion. And what we're gonna do on Thursdays, we're gonna take our ball drop and we're gonna measure the acceleration due to gravity by interpreting our tables. With a known distance, we gotta have that known distance. So you guys do have, I've got a couple of those videos. Our lovely jumping up and down here with our motion on the train. But we did a couple of takes. Second take is better than the first take. But we did a couple of takes to get that. Clearly we're moving on the train, we're in motion, but we have independent motion between the y direction and the x direction. So you can also go through, I've got a Hewitt Druitt video that can go through this whole ball toss very conceptually, just like what we've done here. And we've got that whole ball toss, and we're looking at our individual vector. My vector in my x direction isn't going to change. Isn't going to change. My x direction vector isn't going to change. My y direction vector changes. Because remember, my change in y is going to equal my initial velocity in the y direction times time plus 1/2 the acceleration times time squared. We're getting that same equation of motion that we've been dealing with all along. So you've got that little conceptual video. And I do want to show this one, so I'm going to stop the recording. It's one of my favorites.